Morning. Yeah, they're going to bring one. Builds character. Imagine if you're like in Singapore.
They probably have air conditioning.
It's true. Imagine, I don't know, India. South India in a remote village. What? There you go. Imagine if you're in Berkeley. Yeah. It's hot and humid. It's like, what is this? I feel this wetness in my forehead, and I just don't understand where it's coming from. Right? That's kind of the feeling in the Bay Area, right? It's like, what is this? It's getting there. It's less than a minute. It's 45 seconds. Excited? Yeah. Kirk is better than Picard? Yeah, but because Klingons are like friends in Picard time. 9, 8, 7, 6, 5, 4, 3, 2, 1. Welcome to EE123, lecture 12. Woo! No. Welcome to EE123, lecture 12. Woo! Welcome to EE123, lecture 12. Woo! Okay. The discrete wavelet transform, hopefully, because we still have to catch up on some continuous time. Okay, so before we start, announcements. Midterm 1, this Monday coming up, midterm 1, from 10 a.m. to 12 p.m. Okay, that's where the a.m. changes to p.m. exactly, ends. Okay, and then you go eat lunch. Everything up till to all the materials, including today, but with more emphasis to yesterday, right? But we can ask you questions of even what we covered today. But it's going to be fair. Okay? Now, midterm is kind of like a piece of art. It's like you start this artwork, and then you don't know how it's going to end when you build it. But eventually it's this piece that you create, and so whatever comes out. But so far, I think it's we'll do it. The one thing I guarantee is that you learn stuff, and it's going to be fair. Okay, open everything except electronics. So no electronics, no calculators. You don't need any of these. We'll make sure that you don't need calculators at all. Okay. One other announcement: pre-lab 2. Which is the prefix to the lab that's due next week. It's due this Thursday. And the reason that we wanted you to have it by Thursday is we want you to get all this installing the SDR drivers working when you have SDR software so you can play with it, see how exciting SDRs are. And then you're going to look at different part of the spectrum. If you do it inside, like in the basement of Corey, it's not going to be as exciting as if you do it, let's say, you go outside to the sun, sit down and look at the spectrum. It's amazing what's going on there. Okay, it's amazing. By the way, we'll talk maybe about this on Friday, but did you know that a few billion years ago, there's these two black holes, 30 times the masses of the sun, kind of went around each other at 100-kilometer distance or something ridiculously, and going around each other at a few hundred hertz, and that ripple in space-time slowly moved and passed through Earth a few weeks ago or some time ago, and was able to detect that. Gravity waves. Insane. I'm going to show you some. There's actually a beautiful IPython notebook of processing of those signals that uses exactly what you're covering in class. Spectrum, low-pass filtering, stuff like this, in order to detect those gravity waves. Okay, so we'll talk about this on Friday. Any questions? Who has not started pre-lab 2? Start, please. Okay. Look, I told you, one of the added value of this class is dealing with hardware. That's always, there's issues with this. So you'll become better engineers by understanding how to debug hardware in order to do better processing. The other thing, actually, I have to, let me just go back. So lab one, or in just the labs themselves, there are instructions. But the point is not just follow instructions. The point is also you understand what are you actually doing. And so here's an example. Let's say you run a chirp from 0 to 20 kilohertz, and you see a response that ends at 8 kilohertz. In the second part of the lab, when we tell you to put pulses at 15 kilohertz, it doesn't make sense if your laptop cannot receive 15 kilohertz. So one of the things is you need to understand what are you actually measuring. So if you run through this chirp and see, okay, it ends at 8 kilohertz, it doesn't make sense for the second part to 15 kilohertz, it doesn't work. Obviously, it's not going to work unless you solve what the issues is, but it's not going to work because your system is not capable of doing this. Okay, so yes, follow the instructions, but also try to understand at each step what actually you're doing and how that implies for the future steps. Okay, so some of it will be written, but some of it will be it's part of part of the thing that you need to kind of explore. Okay. What did we talk about last time? Any questions? Midterm, something before we go into wavelet stuff? Nothing? Everything clear? Nothing? What? The past midterm solutions? Just the questions? As you notice, some of your homeworks have midterm questions in them. So we want to be careful of not posting homework questions afterwards, but I think past midterm 1, we can post solutions too. Yeah.
We'll go over the solutions in the reviews.
Yeah. Okay. Yeah, that's it. Any announcement?
Wait, are there 2 reviews? Okay, so on Piazza, it shows that there's 2 reviews, one tomorrow 5 to 6, and one Friday 5 to 6, 521 Corey. We'll go over past midterms.
Are they the same material?
No, we'll go over different midterms.
For these, we'll post solutions, though. Yeah. Okay. All right. So last time we talked about I don't know if we can record those. We can give it a shot, but it might be difficult. We don't have that. We'll give it a shot, but you can also ask one of your friends if that's another option. We can try. Let's say we can try. Yes. Okay. The wavelet transform. Let's move on. Wavelet transform. Last time we talked. What does that actually mean? We're going to do a different space-time decomposition. Sorry, not space-time. That's because of the black hole. We're going to do a different time-frequency decomposition. We have the time-frequency space, and we have the Eisenberg uncertainty principle, which tells us that there's a limit to how much resolution you can get in one of those, and it's always going to be a trade-off. And so you can decompose the time-frequency space into different tiles. The short-time Fourier transform breaks it into same-size tiles. The wavelet transform will break it into different size tiles that will have wider support in time for the low frequencies and more compact support for the high frequencies. And why is that? Because often when we have something that changes slowly, maybe we want to see the small differences in how it changes. If you have something that changes very fast, you want to really be able to, if you want to have something that changes slowly, you don't care so much about how it changes over time because it's slow. Maybe you want to get better spectral resolution for those frequencies. What about things that changes very fast? You want to see how they change over time in a well-defined way. Maybe you don't need that accuracy in the frequency domain. So the atoms, or the building blocks for these transformations, are made of this. The short-time Fourier transform is really a windowed frequency. Okay, a windowed frequency, all of the same time length, but just different frequencies. Those are the building blocks of the transform. You can, when you take a signal and you apply the transform, you basically project it onto these basis functions. Okay, so you have coefficients of those kind of wavy things. Okay, but they're same size in time. For the wavelet transform, you do something different. You have some wavy thing that has some support in the frequency, and in order to get different supporting frequency, you stretch it. By stretching it, you also change its time support. And that's the different thing between the wavelet and the short-time Fourier transform. Here, the window is always constant. Here, you just change the modulation frequency. Here, you stretch it, and by stretching it, you get different frequencies. But you also get different time support. Okay? So that's what we covered last time. Now, there's different examples of wavelets. One of them is the Mexican hat, defined like this. So remember the requirements for wavelets, that their integral should be 0, so they're bandpass filters, but also that their norm is 1. And this signal satisfies this. This is a bandpass filter, has norm 1. And if you integrate over it, it also equals to 0. That's one example. And that's another example. This is called the Mexican hat wavelet. This is called, or sombrero wavelet. And this one is called Haar wavelet. Okay? Those are different bandpass filters that have different selectivity in the frequency. Okay? And they also have different selectivity in time. But what I'm trying to say here is that while the Fourier transform, there's not a lot of options there. There's just frequencies, pretty much. And, maybe the type of window that you're going to pick. With wavelets, there's just so many type of wavelets that you can use in order to represent different signals. For example, if your signal is piecewise constant, a representation using the Haar, these kind of basis functions, may actually fit really well. If your signal is made out of spline polynomials, maybe have a basis functions that are wavelets that are made of spline polynomials, which can have a good representation for it. The Fourier transform is really good at representing frequencies. So if you have discrete frequencies or something periodic, Fourier transform is great for that. But it's not great for something that changes like a piecewise constant, right? Because then it spreads out the frequency domain. So maybe there's an advantage of using these different types. I showed you this example of a chirp, but my point is that there is selectivity in time as well as frequency. You see that there's better selectivity when you're talking about high frequency. You kind of see a lot of structure going on. For the low frequencies, there's less structure in time, but it's more concentrated in the scale. We'll talk about it more when you get there. This is too slow. Move on. Okay, so then we ended up, when I showed you this diagram, this result. And this is really a Mexican hat wavelet transformation of this one-dimensional signal. Again, it's mapped into 2 dimensions. One dimension is the scale, how much you stretch it, how much you stretch that Mexican hat. The other one is translation, where you move it around. And if you look at that signal, it's made out of smooth stuff, but also bumpy stuff. Okay? And if you kind of think of what wavelets are, these are kind of like, it's a multi-scale representation of your object. If I wanted to have kind of a 10,000 view of what this signal is, I would say can look at this cross-section over here. And yeah, it's like it gets intense and then goes low. And absolutely, that's what's kind of a 10,000 view of that signal. It's like it gets intense and then it goes low. But if I want to zoom in and look at the details, like I'm zooming in, all I'm going to see when I zoom in is these bumps, right? Because when I zoom in, everything that's smooth, looks the same, looks flat to me when I zoom in, except for bumps or these, jumps. Those are the details. And so the signal, this decomposition gives you this kind of a multi-scale representation where you get these bumps. You see exactly where they happen, which will not be true for a Fourier or a short-time Fourier transform. You don't know exactly where they happen. Here you know exactly where these transitions happen, but also you get kind of a zoom-out versions of them. So the wavelet transform gives you a kind of a, if you think about this, kind of edge detection at different scales. Okay? It's edge detection at different scales. And so here's an example. This cross-section over here is taking this signal and basically doing a multiply, add. And obviously, when you take something that's really localized in time, you're going to get these bumps that show up whenever you have these changes. Otherwise, everything here sums to 0. So if you have something smooth, you multiply something smooth with something that sums to 0, then you get a really small signal. Except if you have like a big change, and then you get something left. What is the line here? The line here is basically I stretch the whole thing a little bit more. And now I'm kind of doing a bandpass, but it represents lower frequencies, which I'm going to then go through and represent my signal. And then at the bottom, it will be something even more stretched. So represent something that more zoomed out, right, when I convolve it with my signal. Okay? So this really is what the wavelet transform is. Okay? So representing this signal by a decomposition of these scaled functions. Scaled function. That's how you get frequency as well as time. Each one of these scaled function has some frequency support, and it also has some time support. Any questions before we move on? Yep. Yeah, actually, S is small and it increases, right? So the scale is increasing because I stretch it, okay? And this is logarithmic scale, okay, of S. So that's the highest frequency, and in the highest frequency, I have very good also temporal resolution. Okay, I can see where those bumps happen, and as I move down, then I don't know where things happen very well, but I have better frequency support. Okay. All right. So the thing is, I showed you that what we're doing actually is taking a function and then we translate it and scale it. You can also write this as a linear filtering, in fact, because what is translating, multiply, and add? It's exactly like a convolution. So you can represent it as a convolution. So the wavelet transform of a function can be written as the integral from minus infinity to infinity of your signal, and then multiplied by that wavelet kernel or this mother wavelet that is translated. So this is really a convolution operation. So for a particular S, if you fix S, this is actually a convolution, right? Because there's this shift. So you can write it that way. So FT convolved with omega sub S of T. Okay, so for every scale, you get yourself a convolution. So in fact, wavelets coefficients are a result of bandpass filtering. You just filter over and over with different bandpasses. Each bandpass is just a stretch. Its impulse response is a stretch version of it. Yes? Pardon? Here? No. So this is actually without the star, right? Because you have the hat over here. Because you have to flip it. So if the wavelet was complex valued, yeah, it's the conjugate of it. Yeah. So this is the mother wavelet that's not conjugated. When you actually do the filtering, you have to conjugate it. If it's everything symmetric and real, it doesn't matter. If things were right. So this is actually, so it just defines which one is the conjugate and which one is not. And the way that people define it is that they find the conjugate here, and when you filter, then you actually apply that conjugate. Okay. So in the filtering operation, it's going to be the conjugate of that. Okay. Does this make sense? Pardon? Bar is a conjugate. So it's a conjugate of conjugate. Yes. It's okay. So you can interchange. Sorry about this notation. I apologize. Whenever you see star, it means complex conjugate. Whenever you see bar, it also means complex conjugate. If you see H, it's also a complex conjugate. All are equivalent, and I'll fix that in the future. Okay, so there's many different constructions for different wavelets. You can come up with different types of bandpass filters. For example, Haar wavelets are good for piecewise type of piecewise constant signals. If you want to represent something that's piecewise constant with a basis that is piecewise constant, it's ideal in that sense. Because you don't need that many projections in order to you don't need that many coefficients in order to represent it. If you have a signal made of spline polynomials, you can use a different type of filter. If you had something that's completely periodic, maybe that wavelets are not the best case. If you have something that's periodic, you probably want to use a Fourier transform in order to be able to represent it, right? But if you have some signals that are made of piecewise stuff, then the Haar wavelets are actually really good in representing them. Now, when you look at the wavelet transform, it was continuous over. I'm getting warm here. It was continuous over S and U, but then it's also not orthogonal. If you look at each one of these kernels or basis functions for the wavelet, they're not orthogonal to each other. So you can actually come up with wavelet transformations which are orthogonal. And the way to do this is by discretizing your scaling and discretizing how much you shift it. It's still continuous, but your kernel is now going to be concentrated at particular positions in space and time. And I'll give you an example. So this would be the scale. So 2 to the I would be the scale. So S's will be quantized. And also the shifts will be quantized by that. Here's an example. Here's a Haar basis function. Okay, this is a Haar basis function that I'm discretizing at 0, 0. So 0 scale and 0 position. This would look like this if I put 0 and 0, which in fact just gives me the mother wavelet at the finest scale. And it's going to look like this. It goes from 0 to 1. Okay, I didn't put the scale here, but it goes to 0 to 1. The next one of scale 0 and position minus 1, if you put that, it's going to be shifted basically by 1 to the left. Now, why is this orthogonal? Because if you project on this basis function, it's complete. That information you get is completely orthogonal to projecting on this basis function because they don't overlap. And if you want to cover the entire space at this scale, you just representing using those functions. Okay, so those are the functions, and so are discretized. You don't have representation for the one in between. Okay? If you don't have them, then they're orthogonal to each other. When you go to the next scale, you don't just stretch it by 0.1%, or 2% or 3%. You scale it by a factor of 2. If you scale it by a factor of 2, then whenever you have, so this would be at scale 1. So you jump one scale. Now it's twice as wide. It's a little bit lower in amplitude in order to maintain the norm 1. And it's basically your original wavelet only scaled by a factor of 2. So it's stretched by a factor of 2. Now, why are these orthogonal to each other? Well, because if you multiply this basis function with this basis function, you'll see that you got in one period, you've got a plus and a minus. So if you multiply and add them, they're going to sum to 0. As well as the yellow one and this one, they're going to multiply and add with the plus and minus exactly the same area over something that's constant. So if you take this basis function and multiply by this basis function and do an inner product with this basis function, you get 0. If you take this basis function, do an inner product with this basis function, you also get 0. And of course, with these, you get 0 because they don't overlap at all. And then the next scale, you stretch it again by a factor of 2, and so this one is going to be orthogonal to the other scale, and so on and so forth. Does this make sense? So the next one would look like that, where now you got yourself the function shifted by that amount, and again, it's non-overlapping. Does this make sense? So this is a discretization of the basis function. It's still continuous time transformation, but it's discretized in the basis function. So you can take a continuous time signal and project it onto that basis, and that basis will be orthogonal. Okay. So if you actually think, what is the frequency support of each one of those basis functions? So if you look at the finest scale, okay, if you look at the at the final scale, you'll see, or some scale, you'll see that it's going to be a bandpass filter. Okay, so it's a bandpass filter that has a certain support. Okay, at scale I equal m. Okay. Then I'm going to stretch it by a factor of 2. If I stretch it by a factor of 2, what really happens is that you shift your frequency, but also you're more concentrated in the frequency. So frequency shifted to lower frequency, centered around lower frequency because we stretch it, but it's also more concentrated in the frequencies. Right? You have less bandwidth as you stretch it. As you stretch things, you have less bandwidth. So what happens really is every time that you scale those functions, they will cover a lower frequency, but then smaller size of that frequency coverage. Then the next scale would be, again, lower frequency, but more concentrated. And then lower frequency and more concentrated. And then lower frequency and more concentrated. Yes? Yes, but it's kind of like it's a illustration. Of course, if you use square waves, the concentration is going to be around this, but it has a support everywhere in frequency. If you use sinks as bandpass filters, it will be really concentrated. But this is more as an illustration of where is the energy, most of the energy of that wavelet supported, right? But in some way, it will be the same for every, like if you pick a psi, if you pick a mother wavelet, then this will be really the representation. It's not going to be compact, but it's going to be concentrated in those frequency ranges. Okay. So every time you scale, you get narrow, but like you never end. Like you just scale and you get closer, but you never really can cover the entire frequency space. Right? So you need infinite number of basis functions in order to come up with an orthogonal transformation. Just infinite amount. And so the solution for this, how would you solve it? You need maybe a basis function that would put a plug there, that will represent like the missing part that's left. Right? All these basis functions, represent parts of frequency that are decreasing. So as you get to 0, like you never really represent 0. Like you can need infinite number of basis functions to do that. So how do you close the gap? Remember, we have one generating function. One generating function, which is the mother wavelet. It has a certain shape, and we just stretch it, stretch it, stretch it, stretch it, stretch it, stretch it. But it always sums to 0. You can never really represent DC. So in order to represent the entire space, what do you need? What's missing? A low-pass filter. That's right. So if you want to have a orthogonal transformation that you project your signal onto coefficients of orthogonal basis, you can create those by stretching those wavelets till a point where it says, well, I'm not going to stretch them anymore. And then I still need to have some low-pass component in order to represent the low frequencies. Okay? So all you need to do is put a low-pass at the end that will basically plug it. So all of these are generated by scaling the wavelet function. All these frequency representation are generated by creating those wavelet functions. But at the end, you need to plug. So you need another function that has low-pass component in order to represent the rest. Okay, you'll see it in a second. Like it will be much more evident. And so that function is called a scaling function, or the father wavelet, and is representing by phi. Is that phi? Yeah. By phi. Okay. And this is going to be the low-pass component. So if you think of what are the basis functions for a Haar wavelet transformation, you're going to get the mother wavelet, which is stretch and stretch and stretch and stretch and stretch. This is what you're going to use. And then at the end, you're going to close the block by projecting onto something that looks like a block. Okay? When we get to the discrete in a second, I think you'll get what I actually mean. Okay? If those of you are still in the fog there. So all I have now is some function that is bandpass that I stretch it and convolve with my signal. So basically, different bandpass filters. I can make an orthogonal representation, so I can make sure that those filters, if I filter that signal, I get new information, right? That there's no overlapping information between those. And then if I scale and scale and scale, at the end, I need to stop at some point. And if I want to stop, then I need to have the rest represented by a low pass. Here's just a simple example. If I want to represent all information in a signal, if I take a derivative of a signal, does it give me all the information? Can I, after taking the derivative, can I reconstruct my signal back? What's missing? The constant. So I need to, if I want to represent my signal, right, through this transformation by taking a derivative, I'm going to take a derivative, I'm going to store the derivative coefficients, and then I'm going to store what is the mean of my signal. If I have that information, I got all the information I need in order to put back the signal together, right? Does this make sense now? Yes. If you use the low pass, then it's a finite number. So I have a finite scale, so I can stop at a certain scale. That's what I mean. I'm going to stop at, like, if I stretch and I stretch and I stretch and I stretch and I stretch. No, okay, so there's a finite scale. So you start at a particular scale, okay? You start at a particular scale, and then when you stop stretching at a particular, at the end. So there is a finite to how much I'm going to stretch, okay, if I want to represent my signal. Does this make sense? So it's as similar as a derivative.
In time is like an infinite dimensional vector, basically, right?
Pardon?
A function in time is like an infinite dimensional vector.
Sure.
So how can we project an infinite dimensional vector on like a finite set?
No, all I'm saying is that you have a maximum scale that you can go. No, if I finish at a certain scale and then I plug it with a low pass, then that's enough in order to represent. So here's an example. If I take a derivative of an infinite number, I have infinite number of coefficients in the derivative, but with a derivative, I can never represent my signal. I take a derivative of a signal, I only get the derivative, right? If I want to build back my signal, I can't. I'm missing information. The information that I need is the DC, right? What is the mean? If I take a derivative of a signal, I can never represent, I cannot integrate that signal back into its original, right? Because I'm missing information. And so you plug it by putting this low pass. Let me explain. When we go to discrete, it makes more sense. And so I don't want to spend too much time on the continuous time because that's not the essence of this class. But what I would like to say is that all this work on this has started in the 80s by a lot of theoretical work, Morley, Grossman, Meyer, in math and geophysics. They realized that you need to do some other decomposition than a Fourier transformation. In the late 80s, there was a link between, from a signal processing point of view, people started doing kind of what's called a multi-rate type of processing, filter banks, dividing the signal into different frequency representations. And Daubechies and Malat made this connection between this early work to the work that's done in the DSP and connected them into what's now is the discrete wavelet transform. If you want to move from this continuous time of this stretching this continuous wavelet into the discrete, it's not so trivial. And so there's kind of small nuances that you need to make in order to maintain these properties, such as orthogonality and so on and so forth. And let me just go now and move into the discrete, where I think things will definitely make more sense to you. So when we're talking about a discrete, now you have a certain size of signal that you're going to decompose it. Okay? You're going to decompose that signal into coefficients. And it's going to give you a representation in this time and frequency space. So if you remember, we had this mother wavelet in the continuous space. We had this mother wavelet that we multiplied, that we did this inner product and did this transformation. By the way, this looks exactly like the DFT. Right? DFT, you write like this, except here would be omegas, like W sub n to the power of kn. Okay? So instead of W sub k to the power of kn, now we have this psi. This is exactly, this is still this transformation. Okay? It's the same, like think of the DFT would be, just use these W's. Okay? Parameterized by KNN. Or the short time Fourier transform, it will be parameterized by position and also frequency. So it will be parameterized by K and N, where you are in space. Okay? So what you're going to do now is going to have some basis functions that are going to be high-pass filters, and then you're going to scale them so they're going to go lower and lower in frequency. And then you're going to have one basis function or several basis functions are going to represent the lower frequencies. So the same decomposition as we had before for the mother wavelets will give you a coefficients that are called detailed coefficients, where what you do is you have representation of frequency and time that supports high frequencies and has small support in time, compact support in time. Then you go to the next stage where now I scale my function. So that's the first scale. And now I have higher support in time and narrower support in frequency. And then I'm going to have another coefficient which has, let's say, the entire support in time, but some support in frequency. And then at the end, I'm going to get kind of maybe the average of the whole thing. The average of my signal at that window would represent the entire time, but will give me a DC component, which is really supported by frequency. I can do this decomposition, or I can say, well, let me just stop here. I don't want to decompose anymore. If I do that, then I'm going to get, this is called detail, this is called approximation. So I'm going to stop, and I'm going to get two coefficients of approximation. Those represent, this part of time and some frequency, and this part of time and some frequency. Let me explain when we now move to Haar wavelet. when we have a signal of 2. Okay. If I have a Haar wavelet in discrete time looks like this. This is how it looks in discrete time. Okay? It's 1 minus 1 filter. That's the mother wavelet. The father wavelet, so this is the detailed or the mother wavelet coefficients. This is the scaling function of the approximation. This one looks like this. Okay? This is a high pass, and this is a low pass. So if I have a two-type signal, two-length signal, and I want to do a wavelet decomposition, I'm going to project onto the detail, and then I'm going to project onto the approximation. The detailed coefficient will give me a space-time decomposition of, that part. So its support now is 2 in time and 1 in frequency in terms of indices. And then the approximation is also 2 in time and 1 in frequency. Okay, so this is a two-length signal. Now here's what's interesting about this, is that decomposition is exactly like the DFT of a two-size signal. You do a high pass and a low pass, 1 plus 1, 1 minus 1. That is also a DFT of 2, size 2. It's completely equivalent because it kind of makes sense. There are really not many ways to decompose a signal of length 2 into high and low frequencies. Either add them together or subtract them, pretty much. Okay? Now here's what happens when you look, ignore these for a second, when you look at an 8th lung signal. In an 8th lung signal, my Haar coefficients, the first one that I'm going to look at, project onto, is going to be this basis function. I'm going to take my signal, and I'm going to multiply with this one and add. What it's going to give me is going to give me the difference between two samples on the left side of my signal. Okay? If I multiply my signal with this, so multiply that with the original signal, and then add, it's going to basically take the spatial derivative or a finite derivative or a discrete derivative difference between two samples of my signal at this point in time. If you think about it, that's kind of like a high frequency that's localized where? On the left side of my signal. Hence, in the time frequency tiling, it's going to map this block. It's going to correspond to this block. Has a support of 2 wide. And how much frequency has support? Well, it's going to split my frequency into that chunk, pretty much. The next one, the next Haar coefficients that I'm going to compute is multiply and add by this basis function. This will take a derivative, or like a finite differences, that is a little bit to the right. That corresponds to high frequency component that it's over here, located over here. The next one, and note on the indexes, this is the index that has position information. This is the index of scale. The scale is still the same. Now I have Haar that's shifted, right? So I take this basis function, I shift it around, and I multiply and add. That'll give me a difference that is concentrated here. The next one is a difference that concentrated here. So it's high frequency information that's concentrated in the right-hand side of my signal. Now what I'm going to do is I'm going to switch to the next scale. How do you switch to the next scale? You stretch the Haar, right? You stretch it. So how does a stretched Haar look like in discrete time? I can't hear you. 1, 1, minus 1, minus 1. That's a stretch version of the same function, right? So it's going to look like that. But how many orthogonal vectors I have that looks like this? Well, now I have a support over 4. Here the support was over 2 in time. Now the support is over 4 in time. So I'm going to only have 2 coefficients at that scale. One concentrated here, and one concentrated here. Those will correspond, this one will correspond to this. So that's the frequency tiling, time frequency tiling of this part corresponding to here. And this one is the frequency tiling corresponding to here. And what will be the next one? 4 ones and 4 minus ones. That's more stretch, right? And what's the support of that? It's 8. Its support is 8 long. Yeah. Yeah, it is scaled by 1/2, right? In order to normalize. Yeah, absolutely. You're right. So it's scaled by that, right, in order to make it normal. So now its support is, negative and then positive. But now my basis function has a support of the entire signal. And what it's actually giving me, it's giving me this. I mean, it's among the low frequency, the low frequency components. It's kind of that high, it's this bandpass. And then the last one, to plug the whole thing. All ones, right? I cannot stretch that anymore, right? I don't have anywhere to stretch it. I need to plug in the last part. Then I'm going to plug in with that. So this is the Haar wavelet basis function for discrete time signal of size 8. Orthogonal Haar for size 8. These are the basis functions. And so my time frequency decomposition will give me this tiling, which is kind of what I want. Yeah. So this is half, and it's approximate, right? It's like the amount of concentration. Right? So this is half of the space. And all of these represent half of that space. All of these represent the second half. And then these represent the top part of the second half. These represent the bottom part of the second half. And then you split it again.
Is it exactly like that?
Yeah, but I mean, these energy kind of concentration, it's not like it's really just there, right? Because the Fourier transform of a 1 minus 1 is kind of like concentrated in the low pass, but it's like not, it has some high frequency components. It's more the concentration. Okay? So it's an illustration. It's not like, that's like, you probably need to do like a color kind of map. And you would see like, yeah, it's like brighter here and then it goes darker, right? Yeah. Pardon? That's the scaling, so that they're orthogonal. So the amplitude here is 1 over square root of 2. So if you think actually what I did here, okay, if you look at those basis function, this is kind of like a convolution with a with a 1 minus 1, except that I'm skipping every other measurement, right? Because there's like this sweeping thing, right? Like I move my function. This is kind of like a convolution. And if you remember, in the continuous time, we describe things by convolutions. So we can still do that we can compute the Haar transformation using what's called a filter bank. And when we get to filter banks, later you'll see that relationship. Yeah?
What happens if you have a function that doesn't have as many samples as an hour, like you have 9 or 10 or something like that?
Yeah, you can deal with this, but you cannot like split it into 2, right? Like the decomposition is more complicated. It's not dyadic, but like yeah, you can do something with it. But I don't want to spend much of this because this is enough to kind of like break your mind. So if you think about this from a filtering point of view, you can implement the discrete wavelet transform or the Haar wavelet using a filter bank where you define H0 to be one, like the low pass and H1 to be the high pass. And then you pass your signal through these filters. So the top one will give you the approximation. Will give you the low frequency information. The bottom one will give you the high frequency information, right? It's high pass and low pass. And so the question is like, what is the tiling that comes out of this filtering? High pass and low pass. What's the tiling? This is the tiling. I have a support of 2. And I break my frequency space into high pass and low pass. So I break it into half. So my 8-lump signal is broken into time resolution of 2, and it's broken in frequency into half, high pass and low pass. But the thing is, when I do the convolution, I also get the one in the middle. Because with a convolution, you don't end up with 4 and 4. You end up with 8 and 8. And so what you need to do is downsample. So you do the convolution, and then you downsample. And when you downsample, this will give you the approximation or the low-pass coefficient at that scale, and this will give you the detail coefficient, high-pass, at that scale. And now, those were good. This, maybe you want to decompose more. So what I'm going to do is I'm going to take these approximation coefficients and then break it into high pass and low pass again. That breaks it into smaller pieces. That should be wider, actually. This is wrong, actually. Sorry, but remove this line over here and then remove this line over here. Okay, because it's going to have only 2 coefficients. And 2 coefficients. Sorry about that. I'm going to fix it. Pardon? Okay, so when you convolve with, because when we decompose into low frequencies and high frequencies, if we want orthogonality, we're going to end up with 4 detailed coefficients and 4 approximation coefficients. Convolution gives me 8. Right? If I convolve a signal, I'm going to get, so if you think from a basis function point of view, I'm going to get, really what I want is a convolution, but without the one in the middle. Here I'm jumping over one signal, right, in order for it to be orthogonal. If I have the one in the middle, like a convolution will have the one in the middle. And I'm not interested in it, right? So I'm going to jump every 2. That's why I decimate. Because I'm going to throw, if I do a convolution, I'm computing something that I don't really want. Okay? So I'm going to steal 1 minute. Actually, I just want to show you how a decomposition looks like. Okay? This is a signal that I'm going to do a Haar decomposition, Haar wavelet decomposition. This is level 0. That's my signal. I'm going to do a high pass, downsample, and then a low pass, downsample. Those are the detailed coefficient that I end up with, and those are the approximation coefficients. Now, here you can see why they're called approximation coefficients. Because they approximate. It's a low pass approximation of this. Right? So I have from here, from this and this, I can go back and build that. But this gives me kind of edges. I see that edge over here. I see that edge over here. There are other edges, but they were, because they didn't fit exactly and they were cropped away, they might show up in the next scale. Then I take this one and I break it into details and approximation. Right? That's the next scale, the next level. And then I take this guy and I break it into detailed and approximation. And you see why now it's called approximation? Remember, that was the original one? Now, yeah, it is approximation with fewer measurements. It's kind of like zooming out of it. I'm going to take this one, and I'm going to do, again, detailed and approximation. And then detailed and approximation. And detailed and approximation. And at the end, I'm just going to be left. That's the 2, like if you want to represent that signal here with 2 coefficients, I would say that's a good one. High and lower. Right? Pretty much. And so if I put all these together at different scale and I'm showing you the intensity, what you see is something similar to what you've seen before. At every scale, I've got the details. These are the details. And the details represent kind of those edges where things are changing, when things are moving rapidly. And at the end, I'm just going to get, this is the approximation at the end. But you see those are really representing edges at different scale. Now this has all the translations. This is not orthogonal. When I go and I downsample, then I'm going to miss a few. This is too much information. I have like more coefficient than I started with. If I only keep the orthogonal transformation, the same coefficients, this is what I get. And so you got yourself a good representation of the detailed information as well as the approximation at the end. Does this makes more sense? Yeah. That's I stopped here. I didn't really keep on decomposing it. If I kept on decomposing, yeah, we'll have a DC term at the end. I just stopped at this level. Now, the one thing that's really interesting about this is that I can also write it that way. If I just concatenate all these levels together, this is the finest scale.